Hi, so now we will talk about another example that is a binary search code, and you have already learned about binary search algorithm as well. So what we are going to do, we are going to figure out what would be the complexity of binary search algorithm. So let us first try to do it intuitively, and then we will also see it in the code. Okay. So intuitively, what if you want to see what binary search does, it takes in an array of, let's say, size n, and in each iteration it finds out the midpoint, that is a constant work, and accordingly it moves the start and the end pointers. Okay, so let's say start is here, end is here, and after the next iteration this part of the array is discarded. We do some constant work and we reduce our array to size of n by 2. Okay, so we get a size array of size from n, we get an array of size n by 2. From n by 2 we again get an array of size n by 4. Okay, then in the next iteration it would be n by 8, and in the next iteration it would be n by 16. And doing this after some k iterations, we know this array will contain exactly one element. Okay, so after, let's say, this is after in the 0th iteration, this is in the first iteration, this is in the second iteration, this is in the third iteration, and let's say in the kth iteration it is equal to n by 2 raised to the power k. Okay, and we also know that this is going to be equal to 1. So I want to find out how many times the loop is going to work. So effectively loop is going to run k times. Okay, so in k steps I make something from n till 1 by dividing it by a factor of 2. So I can say n divided by 2 raised to the power k, this thing should be equal to 1. Okay, because in the end we are only left with one element. Okay, so I can say n is equal to 2 raised to the power k. That means k is equal to, if I take log on both sides, log of n to the base 2. Okay, so that means the loop in binary search code is going to run log of n times, and that means our total work done is also order of log of n. So the binary search is very fast because this log n complexity grows very slowly, and you can see if you have, let's say, n equal to roughly 1000. Okay, and if you do linear search, then linear search is going to take how many iterations? Linear search is going to take 1000 iterations in the worst case. Okay, but binary search is just going to take 10 iterations. Okay, or log of 1000 to the base 2. This is going to be roughly approximately 10. Okay, so if n is, let's say, 10 power 6, so what is this value going to be? So it is going to take 10 power 6 iterations. Let's say you do linear search, but binary search is just going to take how many? So I can say it is nothing but log of 1000 and square of this term, it is 2 log 1000. So it is roughly going to take 20 iterations. Similarly, if you have 10 per 9, then it is going to take 10 per 9 iterations, but binary search is going to take log of 10 power this is 10 power 3 raised to the power 3. So this is just 30 iterations. Okay, in 30 iterations you can reduce a array of size 10 power 9 to array of size 1. That means it's going to be very fast. Okay, and another thing I can tell you is when you talk about online judge. Okay, so in an online judge you roughly have a time limit of 1 second. Okay, 1 second means your program can run up to 10 per 8 iterations. Okay, or this much instructions can be executed roughly. Okay, so depending upon the processor. So mostly for most online judges the processing power is this much available. So if you have a code in which you're doing a work of 10 power 9, okay, so and you're doing something in linear time, so how much time you are going to take? So 10 power 8 takes 1 second. That means 10 power 9 is going to take 10 seconds. And if your time limit is 1 second, then this 10-second code will not work and you will get a time limit exceeded error. But if you use binary search on a search space which is this big, 10 power 9, it can reduce the number of instructions to just 30, and these 30 instructions can be executed very fast. Okay, so in 1 second, 10 power 8 instructions take 1 second. That means one instruction takes 10 power minus 8 seconds, and 30 instructions will take 3 into 10 power minus 7 seconds. That means this is the time that you will take to execute a code in which you are using the logarithmic complexity on an order of 10 power 9. Okay, so this is how we will actually use this analysis. Okay, so I hope you are getting this. And now this is the code of binary search, and what we have done, we have computed how many times this loop is going to run. So I hope you more or less understood this. There is one more method to compute the time complexity, and that is by making equations. Okay, let us see. So let me say that t of n is the code, is the time to do a binary search. Okay, so what I do to do binary search, I find out the midpoint, I do some comparisons, that everything that takes a constant time of k. Then I said I reduce my problem from problem of size n to a problem of size n by 2. So I can say in order to do binary search in this problem, the time taken is t of n by 2. Okay, that's it. Now I can say t of n by 2 is nothing but again some constant work plus t of n by 4. Okay, then I can say t of n by 4 is nothing but again a constant work plus t of n by 8. So I can keep on doing this till I get t of 1, which is again constant work plus 0. Then if I add all these equations, then you can see these values will get subtracted or removed, and t of n is left as summation of k. And how many such equations I am going to have? So I'm going from n to 1 every time by dividing by a factor of 2. So I'm going to have log of n equations. Okay, so it becomes k into log n, and you can see this is nothing but order of log of n. So that's it. That's how we can also derive the complexity mathematically. So I hope this is clear, and I will see you in the next lecture.